In this video, we're going to look at two problems which seem very similar to show you that there are actually a few differences which are potential pitfalls for you. So in this iteration of the problem, I have a bar which is pinned about the left end. It's got a mass M, it's got a length L, and I went ahead and figured out that it's going to be rotating about the pin, so we're going to need the moment of inertia of a bar about its end, and that's 1/3 ml squared, which is what I have here. Yeah, 1/3 ml squared. Now, what I'm also going to tell you about this bar is that you're looking at it from above, right? So while gravity, of course, is going to act on this bar, gravity is going to be going sort of into the page. And maybe you can see that for this motion, that's not really going to affect our rotation. Instead, what I've done is I've sketched a little bitty rocket engine to it, right? That seems strange, but we're going to go with it. We have a rocket engine, and we're going to assume that this rocket engine is so small, in other words, it doesn't have much mass, so that it's not going to appreciably affect the moment of inertia of the bar. That's a strange little assumption, but we make it a lot. We've got a small little booster engine here that's not going to affect the moment of inertia of the bar. And what I'm going to do is ask for we're going to start this from rest, and we're going to ask for the angular velocity when it is in the upright position right here. So notice we're going to rotate through an angle that is some delta theta, which, as you can see, is going to be some version of 90 degrees or pi over 2. What we're going to do is define positive directions when we get our free body diagram on here. But if I just look at this system and I notice that the thing is going to rotate, in this case clockwise, I'm probably going to go against the convention and call that positive, just for the simple fact that I don't like keeping track of negative signs. But let's see when we get there if that's a good choice. So here's my free body diagram. It's basically already done here. I've got this rocket, which is going to produce a constant force attached at the midpoint. It's going to have a support force over here at the hinge. But now I need the geometry. Right, this is L over 2. I'm basically duplicating what I had here. This is basically a free body diagram. But once I do that, I can now sum the torques. Sum the torques is equal to I alpha, right? First thing I'm going to do is find alpha. Well, I guess the first thing is figure out where I'm going to sum the torques about. I'm going to choose this point because it makes the support force go away, and I'm also recognizing that physically it's rotating about this point, so that seems like a good choice to sum the torques about. If I do that, the support force doesn't appear. The only thing that appears is this rocket engine applied perpendicularly at a distance of L over 2. All right, so I do that, and I get force of the rocket times L over 2 is equal to I, which is here, alpha. So I get 1/3 ml squared. That's my moment of inertia times alpha. Now, I'm going to go ahead and explicitly say I'm going to let clockwise rotation here be considered positive. Again, I just don't want to keep up with the negative signs, so I'm going to flout the convention and let clockwise be positive. If that's the case, I can immediately solve for the angular acceleration. I've got 1L here and 2L here. Multiply by 3 and divide by ml, which is what I have left. And I get 3 over 2. And then in the numerator is going to be FR over ml. And that is going to equal alpha. Let me see, make sure I got everything over. Multiply by 3 to get rid of the 1/3. Divide by the m and l, that's here. Yeah, so that's alpha. That's my angular acceleration. Now, what I said was that this force is constant, this mass is constant, this length is constant, this is all constant. That invites me to use kinematics for the to find the angular momentum. I already said I have this delta theta. Now let's make that explicit just from the inspection. I can see that delta theta is equal, or what I said was 90 degrees, but remember to use angular quantities, I need radians. So 90 degrees works out to pi over 2 radians. Now I can find a kinematic equation that relates alpha to angular displacement to find the final angular velocity, which is what I want. So that's probably going to be this one, omega final squared is equal to omega initial squared plus 2 alpha delta theta, right? I'm starting this from rest, so that goes away. And what I'm left with is omega final squared is equal to 2 times alpha, which is here, 3/2 this force over ml, that's alpha, and then delta theta, which is pi over 2. And I'm going to lose this pair of 2's, and so see what I have left. That's going to be equal to 3 pi FR, and then over, lost that 2, but I still have this one, 2 ml. That does not look very much like an L, but there we go. If you are watching this video and you've already done angular momentum, please notice this is not angular momentum L, this is length of the bar L right here. Sorry, I probably should have picked a script L here. But this is not angular momentum, this is the length of the bar. And then that's omega final squared. To make that into omega final, just take a square root. No big deal, okay? So that's this problem. Now, let's do a slightly different problem, which looks really similar, but in this case, this is from the side, and I've got gravity acting at the center of the bar. So I still have a support force over here. I no longer have this rocket force. Now you might go, well, this is going to be the same thing because gravity's constant. This force from the rocket was constant, so I'm going to get the same thing. And if you said that, that's understandable. I've made that mistake myself. But in this case, we're going to see that that doesn't quite work. And it doesn't work because gravity is constant, right? When I say that this force is constant, what I really mean is that the magnitude of the force is constant. Notice, as that bar swings down, because I'm assuming the rocket engine is, bolted down to it, the rocket is going to turn right along with the bar, and it will always stay perpendicular to the bar. That is not the case with gravity. The bar is going to turn, but as it turns, gravity stays straight up and down, right? So let's see if we can figure out how that plays out. I've still got the same moment of inertia. I'm still going to sum the torques about this point. I'm still going to ask for the angular velocity when it swings down through the same displacement of pi over 2. But now I've got to be careful. So sum of the torques is equal to I alpha. Let's start here and see what we can come up with. Sum of the torques, I'm still going to sum it about this point, so the only thing contributing is gravity. But I'm going to write this, mg sine theta. Why am I going to write mg sine theta? Well, we'll see that in just 1 second. That's equal to 1/3 ml squared alpha. Now, I look at this and I go, well, that seems to be constant, but the question is, what about theta? Theta is actually not constant, right? Because this bar is swinging down, because gravity stays up and down, there is less and less of gravity that's perpendicular to the bar as the bar swings down, right? If this is my bar and gravity's here, let's let the bar swing down into this position. Gravity is still here, right? And so the amount that's perpendicular has decreased. In the initial position, it's all perpendicular, but as I swing down here, only some of it is perpendicular. When I get here, notice none of it is perpendicular. So while gravity is a constant, The amount of gravity that is perpendicular to the bar is not constant. So while I can solve for the angular acceleration here, in this position, sine theta is going to go to 1, theta is 90 degrees, right? In this position, immediately after I release it, I could solve for the angular acceleration in this position, but as soon as it starts to move, my expression, if I leave out this sine theta, becomes increasingly wrong, right? Okay. So the angular acceleration turns out, in this case, to not be constant. Therefore, I cannot use kinematics. What can I use to find the angular speed here? Well, energy comes to mind, right? Remember the conservation of energy. Kinetic initial plus potential initial is equal to kinetic final plus potential final. Well, if I'm starting this from rest, kinetic initial is 0. And the only thing I have is gravitational potential. So I'm going to unpack this term in a second. I'm going to set my 0 point such that when I get in this position, up and down, I have no more potential, and that will go away. So before I get to this potential, let's unpack what I might possibly have for kinetic at that point. I might have 1/2 mv final squared, and then plus 1/2 I omega final squared. I could have rotational. And because I have this thing pinned, it turns out rotational is all I have. I'm not letting this translate because it's pinned. Therefore, there is no translational portion. It all goes into rotational. Now, what about this? There's no rotational gravitational potential energy. It is the height of the center of mass above your 0 position. Now, when this bar is straight up and down, the center of mass is still going to be at the center, which is right here, which means I start out at a height of L over 2. Make sure you can see that. Yeah, I start out at a height of L over 2 above my 0 point. I'm going to set my 0 point here. I'm using the center of mass for that. I start out at this height L over 2 above it, just halfway up the bar. Okay, if you need to stop and think about that for a second, please do. But if you have that, I'm going to write potential energy mg L over 2. Now, I need to unpack this stuff. mg L over 2, that's mgh, is equal to 1/2 from here, 1/3 ml squared, right? I'm using this moment of inertia because I'm still rotating about the end. 1/3 ml squared, that's my moment of inertia, omega final squared. Omega final is what I'm looking for. So let's see what I can do. I've got an M, I've got 1L, cancel that L. Let me just clean up what I have. This is G over 2 is equal to, it looks like L over 6, right? 2 times 3, omega final squared. Move this over, I get 6G over 2L, which is the same thing as 3G over L. That is equal to omega final squared. Therefore, omega final is equal to root 3G over L. All right. Half the reason I'm doing this video is because in class today, I characterized this incorrectly. I got this question and this question confused in my mind because I only had time to do one, and I wanted to do I wanted to do this one, and my mind went to this one, so I solved this one as if this was constant. So like I said, it's a pitfall that anyone can fall into. I fell into it today. Just be careful when you're dealing with gravity. Gravity is constant in magnitude and direction. Therefore, the torque it exerts on a system could change if that system moves. For this one, The rocket engine is constant in magnitude, but the direction is not constant. The direction follows the bar, so this turns out to produce a constant angular acceleration and a constant torque. Gravity doesn't.